So that's the protocol layer. So the way you think about it is that there's a whole set of peers in the world, and then your software just starts. You just start your little server, and somehow it needs to find them, open connections to them, and then keep a live discussion with it, so that with all these other peers, so that you can keep connected to them, and then know when stuff happens on the network. In theory, they're supposed to tell you when stuff happens, and you're supposed to do something after that with that information. So the protocol, you have kind of two different parts to it. There's the data format, what goes in, what goes out, and there's kind of the non-purely data part of it, which is in response to that message, I have to send that message, and after that I'm supposed to send that message. Or I'm expecting that message or something like that. So the message structure, all messages have a header. So I think you've touched a little bit about that, right? So I'll go quickly, but all the messages have a header that gives like some generic version information. You have common data formats. Everything is in little endian and not big endian. And then the common data formats are variable size integer, for example. So you need to understand what that is when you implement it. In which format the addresses are, like the network addresses. There's also a format for an inventory of things. So say you request a series of transactions by hash. That's an inventory. Or you ask for a series of blocks by hash again, that's an inventory, and every node will reply to you with the actual content that you requested. And then you have all the different message types. So you have the handshake, which I think Ryan talked about, which is you just open a connection to a new peer, open TCP, and then you're going to send your version. You're expecting another version back, and when that version is back, the other peer is expecting a final version, which is the one that's going to use for the overall communication. That's kind of handshake thing. And then from a protocol standpoint, you have all the SPV specific part, you have alerts, like everything that's happening on the network. Well, not everything actually, but there's occasional, pretty rare on Bitcoin alerts when something happens and an emergency message needs to be communicated, etc. So for a basic communication standpoint, what's the networking part of your full Bitcoin node implementation or whatever your blockchain wants to be, we'll have to bootstrap, so find peers. So historically, this was done in a kind of odd way through IRC. Now it's done through DNS, where you just look up a DNS record, you have a whole bunch of IPs, and you connect to those, and you try to see what happens. So the idea is your software is going to start, and it's going to look up a DNS record. So like if you don't have any connections, for example, it's going to fail at that point. It's going to look up a DNS record. DNS record will return a whole set of IPs for that record. And then you initiate connection with every single one of those. Open TCP connection, start handshake. And then when the handshake is successful, usually the first thing you'll do is ask for more peers. Because most implementations try to not connect mostly to that first set of seed peers, because everybody will want to connect to them, right? Because it's a seed. So instead of trying directly to connect to them and maintain a connection with them, you can just go ask them for a list of other peers to connect to and kind of leave them alone after that. So that's kind of the bootstrap. At this point, now you're connected to a whole set of peers that can be pretty much anywhere in the world. And then you have to maintain those connections. So some of them will ask you for some transactions. Some of them will send you transactions that they've just seen, and then you need to process them and acknowledge them or whatever. Well, actually, there's no acknowledgement, but you just need to process them. And when you get transaction, you send it to them if they haven't sent it to you yet, all of that. There will be, in a distributed peer-to-peer network, there's always bad actors. So there will always be like peers that have been tweaked to try to attack the network. Some that are going to try to flood you, send you bad data, and generally also they can like ask you for a lot of data, right? So you can be contacted and then ask and ask and ask and ask and ask and sort of flood your network connection that way. And you can see that already, at least for Bitcoin, the full Bitcoin node requires a fair amount of resources because of that. So there's a lot of throttling that's happening so that it doesn't completely flood your network connection. So again, in your peer-to-peer code implementation, once you've done all the handshake part, implementing all those messages, then you have to worry about how do I protect my own node. So how do I not get flooded? How do I validate all the messages properly and all that? So that's basically all of what the peer part will do. It also maintains all those connections with all those peers, so usually you want to, if you shut down, restart connecting to the same set of peers. If you thought that they were good the first time, then you might as well keep them and all of that. Now the transaction pool, so that's the live part. So you send a transaction from your wallet, or somebody else has sent a transaction from their wallet, or there's a bot, like a trading bot, and the bot keeps on sending transactions on price events usually. All of that ends up as a whole bunch of in-flight transactions, and anytime they touch a peer, the peer will relay them. If you think that the transactions are valid and standard, will relay them to all its known peers that don't have that transaction yet. So that's everything that's in flight. So the pool is just storage of all those in-flight transactions before they make it into a block. It has to deal with orphans, which are transactions that are reference another transaction that you haven't received yet. So like if you have, like say, a trading bot again, it can send transaction really rapidly. So you may receive a transaction that reference another that you haven't received yet. So you have to kind of deal, like keep them on side, and then when you receive the one that it depends on, then you can add it into the pool. And then you validate all these transactions. So there's a fairly convoluted validation logic. I was thinking I was like about it. And then relay them if they're standard. So again, you have a pool, you receive all those that communication from the peers. You get that transaction, validate it. If it's not an orphan, if it's not a double spend or anything like that, add it to your pool. And then if somebody asks, well, what transaction do you have in your pool? Can you send me this transaction? You will send it, and then you also relay this transaction as soon as you add it to that pool. You may want to maintain also an address index. So that's the more, I guess, user-friendly maybe, or not as on protocol-only oriented implementation will want to maintain which addresses have what transaction. So say you want to do a service like ours, right? And you say, I want to know what the balance in the list of transactions on that address. Well, if you don't check the pool at all, if you don't check the in-flight transaction at all, then you will have returned the wrong balance and outdated information. So you have to have a specific view of addresses as far as they impact the pool. The blockchain. So the blockchain is kind of the block equivalent of the pool, but in the sense that it receives data, right, validates it, and then adds it to some kind of storage. But the main difference is that the pool is simple. There's no real ordering or anything. The blockchain is a little more complicated in the sense that all the blocks need to be ordered, and then you have to deal with forks. So anytime a new block comes in, you're going to be worried about, well, so first validating it, but then does it fit in the next slot on my blockchain? Does it reference the latest block, or does it reference a past block, in which case it's a fork?
So I guess you have two meanings of blockchain here. You have code, which is processing the blockchain, and then there's the blockchain itself. So it almost seems like you're mixing it up a little bit here.
Yeah, maybe I should clarify that. So the question is that they're both the code that handles the blockchain, and then the blockchain as abstraction. So this talks about the code that handles the blockchain. So again, the scope is we're like as a thought experiment making that implementation of a full Bitcoin node, and then you have to implement the part that takes care of the blocks and chain them. So that piece of code will again take the blocks from the peer-to-peer network, accept them in the seem more or less valid, and then really validate them, so it will validate things like the proof of work and all sort of things. And then if the block is valid, fits into your chain, then you will relay it to your peer-to-peer network. So it's again kind of the same thing as a pool, it's just a different data structure underneath, it's a blockchain. So it handles the ordering of the blocks, and those are only backward pointers, right? So you have to make sure that all the backward pointers are well ordered. And then forks when backward pointers point toward a block that's not the latest. And this, so again, assuming you want to do that implementation and you have to deal with addresses, then there's also some sort of trickiness that you can think about when you deal with forks, and a fork end up being longer than the one you're on. So you add, right? Like you have like several blocks. And then you have a block that comes two blocks back. Too far, so good, nothing to do. That blocks there's the next one that gets added to it, and then another one. Then it becomes the longest chain, so you need to swap. Again, assuming you're doing a service like ours, or you're just trying to maintain your own addresses or whatever. Well, like all the transactions that were affecting the addresses you were interested in now became potentially invalid, and it's the other set of blocks that have two transactions, or other sets of transactions. So you kind of need to handle all of that potential swapping around, and impacts on downstream calculations like addresses. Yes.
What's the height of the block where you finally say, okay, this is the new chain that I should do?
So the question was, at which height of blocks do you say, okay, that's the main chain, right? That's the final chain. Well, there's no real height. There's no threshold at which you say that's the definite one. There could, like in some parallel world, there could be a fork that goes on forever. Sorry. So if all the miners somehow decided to split at 50-50 exactly, then you could have two forks going on forever. And it's somewhat happened in the past with, so I forgot which version it was. I think it was 0.6, but I'm not sure. Where there was a little difference in the consensus between two versions of Bitcoin Core. And so the blocks that were produced by the new version were not accepted by the old version. And that happened where a lot of blocks were produced still on the old version, a lot of blocks were produced on the new version, and so you have two chains that evolve probably pretty far, up to 30 and some blocks, and that's the longest fork that ever happened. But if the miners collided and somehow decided to split by 50-50 and each have their own chain, then it would be totally forever and ever, thousands of blocks. So there's no end to it, and you could now send a block that's 5,000 blocks back, and a fork on 5,000 blocks back. It would be offline right away, but it would be still valid by blockchain standard. Right. And block validation. So one of the important job of all that. The blockchain itself and validating block is maintaining what's the current difficulty level. So when blocks are produced, right, they have to, part of the mining algorithm, they have to be, to have a hash that's under a certain value. And that's what's called the target, and then the difficulty is just an inverse of that. But anyway, that's what's called the target, and your block, the hash of it has to be lower than a certain value. That value is also a certain form of consensus over the network. Every single peer will measure, okay, how fast have blocks been produced and how fast they're supposed to have been produced. Because normally the Bitcoin blockchain is tuned for every 10 minutes. Let's say the Dogecoin blockchain is tuned for every minute. So theoretically, say for the past 2,000 blocks, we should have had a block for Doge every minute. And we ended up having one, say, every 2 minutes. So we're going to tune the difficulty so it becomes easier to produce blocks, and then blocks can come faster. So the blockchain implementation needs to deal with that because it needs to validate those blocks and validate that they have the right difficulty. So the validation has a lot of logic. That's kind of maybe one of the most difficult part of, not difficult as in technically difficult, but more difficult as in putting your hair out difficult, in the sense that you have so many different validation rules for a little bit of everything, and you need to agree on all the other peers about everything. Otherwise, you have the risk of a fork, you have the risk of refusing a transaction that everybody accepts, or refusing a block that everybody accepts, and then basically you don't have the same blockchain as everybody else, which is kind of a problem. So the validation goes mostly through the script, which I've mentioned before, right? You need to validate the script, you need to validate that the transaction has the right to be spent. And then you have tons of rules. As I was saying, there's a max money, for example, a transaction or an output can't have more than a certain value of coins. You can't say like the largest ever value. There's limits.
What is that max again? Is that because of the inputs?
The output. So both the maximum of a transaction, but also a single output has a maximum value that you can't send more than. And I'm not completely sure as to why it was accepted, because that's way back when kind of rule, but my best guess would be to avoid a massive, because that would be unhealthy from a network partition standpoint, right? Avoid a massive amount of Bitcoin to transit all at once.
There's a maximum number of Bitcoin as well.
Yes, so there's a max number of Bitcoins overall, but the max amount is lower, much lower than that, yeah. I mean, still much more money than any transaction has been made, of course, because it can be sent, but it's still much more than the biggest transaction. There's a max in the number of signature operations. So signature operations is probably the costliest part of validating a transaction. So, and it's of course a good vector for denial of service attack, right? Like say you sending scripts in transactions is like sending code all over the world, and then just seeing what happens. So a good way to, if you wanted to attack that whole network, would be to send really expensive script to execute. And then you send it all over, and then, well, the whole network is going to call to a halt, and basically your attack is successful. So signature operation is the most expensive one, and you could chain them, like verify signature after signature after signature after signature. So there's limits on the number of signature operation that can be put in a script, in a transaction, and in a block. So even in the block, there's a limit on the number of signature operations that can be in it, which is kind of interesting. You have to validate the proof of work itself. So as I was saying, is the block, as a miner emitting this block, really done the work he or she was supposed to do to produce that block. Then you have to validate like, the coin base, right? The reward that goes to the miners, right? Well, the miners produce the block, and they give themselves the reward by inserting that first transaction in the block, which is a Coinbase transaction, and they could put any value in there. They could give themselves 10,000 Bitcoin. They could put themselves whatever they wanted. And so the whole network has to validate that that amount is not the 10,000 Bitcoin. It's actually the reward that's supposed to be right now. And the reward changes every 4 years, I think. So you need to have that amount that depends on the time span and everything. Yes?
And if that's invalid, what happens? Because that's already been added to the blockchain, right? The
Yeah.
miner would have already added it, right? So it's a part of the blockchain.
Yeah, so the block will be dropped. Like, the block will not be added to the chain. So if you try to send a new block and the reward is 5,000 Bitcoins, then no nodes on the network will accept your block.
So the miners only create the block. The network needs to accept that block.
Yeah,
for it to be
exactly.
part of the chain.
Exactly. So yeah, the clarification is that the miners produce a block, but everybody needs to accept it to put it as part of the blockchain. Again, another way to see the blockchain is a consensus algorithm. Is that you have a wide network of different peers that have no prior knowledge of each other, that can be hostile, and somehow you want to end up with a global consensus of what's the truth. That's what the blockchain is. Yeah, and after that you have all kind of different things that you need to verify. Which does the value of the Merkle root match the transactions that are in the block? There's even rules about like minimum fees, maximum fees, all of that, and verifying the signatures, which is more part of the script. So now mining. Well, actually, we were just talking about it. So again, that's probably a quick review of what you saw already before, but just so mining is getting all the transactions. So you have this live set of transactions that live in the pool and that you receive. Like people have sent it to you, and you keep them on the side. Now you want to produce a block, so you take all of them and you build a block header with them. So the only thing you need, that's kind of the magical thing, well not magical, but the really interesting thing, is that the only thing you need to do to mine is produce a block header. After that you don't really care about the transactions. You don't care if there were 2 transactions in your block or only 1 actually in your code base, or if there were 100 transactions in the block. The mining in itself is absolutely the same. The only difference is that when you produce the miracle root, so like fold the hashes of all the transactions into one and put that in the header. So when you produce that miracle root, well, the miracle root will be different. But after that, the header is the same, and that's what you're going to hash. And whether the block is for, what I was saying, 2 transactions or 10,000, it's the same thing. So you get all those transactions, compute the miracle root, build a block header, and the block header will have, of course, the miracle root, but things like the block, the number of transactions in the block version, a couple things like that. And then you hash that. Depending on your blockchain, people chose different hashing algorithms. So Bitcoin is 2 times the SHA-256. Litecoin is crypt, Doge is crypt too. And so you hash it. Hash gives you can see it as an hex string, but you can also see it as a really, really big number. And you just have to make sure that that really, really big number is smaller than the value that the network agreed upon. So statistically, that number will be more or less fully random, right? Like when you hash something, you get more or less a big random value. The point is that it's kind of pretty unique to that value you gave originally, but to the document you gave originally, but that value is pretty random. So statistically, if you have, say, 10 zeros, right, and then you need to find a value that's lower than 1 to the 9th, right? Then you will have to do it 10 times. That's how you kind of calculate that statistically, right? You may have to do it 1 million times, and if you're really unlucky, you won't have to find anything. But on average, you will have to do it 10 times. So that's kind of the underpinning of the target and the hashing, and why it's difficult is that you will, depending on what's the target value you need to find, the lower bound of your hash, then you will have to calculate a lot and a lot and a lot and a lot and a lot of hashes to all of a sudden miraculously find that hash that's lower than the value you were looking for. And that's a pure random brute force dumb let's hash tons of time game.
Matthieu,
Yeah.
what's the incentive for the miners to add new transactions as they're coming in to hash? Because I would have thought there'd be a performance hit if they're hashing, and then a new transaction comes in, they sort of have to move everything over and start again.
Yeah, so the question is, what's the incentive for miners to add any transaction at all, right? Like compared to
once they start hashing after they've got, say, the first transaction, what's the incentive for them to add the second transaction? Because I would imagine it would slow down their hashing.
Oh, okay. So the question is,